Okay, so this video is for Miss Vaughn's pre-algebra class. This is the part 1 of the quiz review for sections 4.5 and 4.6, which is arithmetic sequences and geometric sequences. I am pretty sure I have not put part 1 up. I tried to record it yesterday and I don't think it worked out. So I might be duplicating myself, but I'm going to do this in 2 videos. Just do your best to get through them. The first section, I made a little sheet that I sent home for you guys that gives you sequences, and you need to determine, is this sequence an arithmetic sequence, geometric, neither, or both? So let's look at the first example. So in the first one, we have a sequence that goes from 12 to 9 to 6 to 3. So hopefully you can see that this is an arithmetic sequence that is moving in the negative direction because it's 12 minus 3 equals 9, 9 minus 3 equals 6, 6 minus 3 equals 3, and then so on. So we see that we're subtracting 3, which makes it an arithmetic sequence. Okay. For number 2, you have 1 to 6, 6 to 11. Well, we know that 6 times nothing equals 11, unless you have maybe some weird fraction. So you are adding, hopefully you see, you're adding 5 to each term in the sequence to give you the term in the next sequence. So again, we're adding a number, so this is an arithmetic sequence. Okay, the next one, you have 1, -3, 9, -27. So hopefully your first indicator is the fact that this is alternating negative and positive, which means you are multiplying times a negative number. So in this case, it's -3. So 1 times -3 is -3. 3 times -3 is 9, because we know every other number is going to be positive because negative times a negative is positive. So because we're multiplying, it's geometric. All right, so let's look at the next one. We have 2 to 5. So we know that's +3. 5 to 9 is +4. 9 to 14 is +5. So this is going to be some sort of adding sequence, but we're not adding by a common value. So remember, it's increasing. So this is neither. Because it does not fit into the definition of arithmetic or geometric. Now, in this case, where it's all the same number, this is an example where it would be both. Because in this case, you can both add 1 and multiply by 1 to get the same number. No, wait, that's not right. Hold on, what am I doing? Oh, you're adding 0. Sorry, ignore me. I'm confusing myself. 0 is still a real number. So it means that your difference is 0, your ratio is 1, but that does mean that this is both an arithmetic and a geometric sequence. Okay, all right, so let me switch share to the whiteboard that I have, or in this case, Blackboard. Maybe. I'm going to give my internet a second to catch up. All right, so now I'm going to move on to the number theory worksheets that I sent home as well. These are from the student activities book that I have, where we are only doing the odd problems. So today we're going to cover number 1 through 15 odd. And excuse me. And see what we have. Okay, so for number 1 and 3, what they're asking for is the first 5 terms of the following recursively defined sequence. So we know this is more than just a recursive formula. It's a recursively defined sequence because number one, they give you a value for the first term in your sequence. And then they give you the recursive formula for that sequence. And the recursive formula includes your, let me write first, n-1 plus 3. It includes your difference, your common difference. So in this case, they've given us the value for a1 is 4. And then this positive 3, this is your common difference. And then also remember what a n-1 is. That is the term at the previous position. So, oh, that was weird. So a(n) is the term at position n, which could be any position, whatever we're trying to calculate here. And then a(n-1) is the term at the previous position. Whereas we can see that the term at position 1 is 4. And we're being asked to calculate 2 through 5. So A2, which is this guy, equals the previous position, the term at the previous position, which is A1. So that's 4 plus the common difference, which is 3. And we end up with the term 7 at position 2. So position 3 is the term at position 2, which is, we just calculated, that's 7, plus the difference. Why did I write D? Cannot talk and write at the same time. And that gives us a term of 10. The term at position 4 is the previous term, 10, plus the difference, which is 13. And then our last one, A at position 5 is 13 plus 3, the difference, which is 16. So the full 5 terms of our sequence here are 4, 7, 10, 13, and 16. Okay, number 3. Same thing. Let's see what we have here. Number 3, they give us the definition of the term at position 1 is -2. And then our recursive formula is an equals a, or the term at position n equals the previous term plus 4. All right, so a2 equals the term at position a1, which is -2, plus our difference, which is 4, which gives us a value of +2. A3 is +2, which is our term at position 2, plus the difference is 6. The term at position 4 is the 6 plus the difference, 10. And then our last one here is 10 plus the difference is 14. Therefore, our final sequence of this recursively defined formula, or recursive definition, is A1, which is -2, A2, which is +2, A3, which is 6, A4, which is 10, and A5 is 14. And that is our sequence. Okay, so number 5 and 7 ask for the first 5 terms of the explicitly defined sequences. So remember, with explicitly defined sequences, we actually don't have to find the terms in order. We could find any term using an explicit sequence, but in this case, they just want us to look for the first 5, but we're going to use the explicit formula instead. So for number 5, they have given us an equals -1 plus n-1 times 3. So I want to show you the explicit arithmetic formula. You have this in your book in section 4.5. It is the term at position n equals the term at position 1 plus the previous position number times the difference. And you can see, if you compare these two formulas, you can see where values have actually been plugged in to number 5 that give you the value of the term at position 1, which is -1, and they've given you the difference, which is 3. So A1 and the D, their values, their terms are already in the formula itself. That's why you don't need a definition for A1 because they've given it to you right here. Okay, so now let's go ahead and solve it. So this tells you that A1 equals -1 because it's right there in front of us in the formula. A2 equals -1 plus our n, which is 2. See this right here, this is n. 2 minus 1 times 3. Or you can just go ahead and know, if you're looking for the term at position 2, that this is going to be the position number of the previous position, which is, in this case, position 1. So it's -1 plus 2 minus 1, which is 1 times 3. So oops, goodness gracious, all day. A2 equals -1 plus 3, which is a +2. A3 equals the term at position 1 plus 3 minus 1, which is 2 times 3, equals -1 plus 6, which equals 5. A4 equals the term at position 1, which is -1, plus 4 minus 1. So it's the previous position number, which is 3, times 3, equals -1 plus 9, which is 8. And then the last one, the term at position 5, is the term at position 1 plus the previous position number, which is 4, times the difference, which is 3, gives us -1 plus 12, which is 11. So our final sequence is -1 times 2, or excuse me, and then 2, and then 5, 8, and then 11. I know we're doing this the long way, but we need to learn this process first. Obviously you can look at the starting term, -1, and you can see the difference, which is 3, and just do -1 plus 3 is 2, 2 plus 3 is 5, 5 plus 3 is 8, 8 plus 3 is 11, and that's fine if you're looking for the first 5 terms. Like we said in class, if you are looking for term 362, obviously you don't want to have to go through this process 361 times. So you use this formula to just plug in that position number. We'll do a little more of that in just a second. So let's go ahead and do number 7, and then we'll move on really quick. So number 7 says, okay, this number 7 has given us a simplified formula. It says AN equals 2n plus 6. All this is it's that explicit formula reduced. So if we had AN equals A1 plus n minus 1 times D, you can see how that would simplify into a value of n plus a whole number. So that's where that came from. This is your original formula. It's fine. You don't necessarily have to figure out how that worked right now, because it gives you everything that you need to determine the terms in your sequence. So for example, if we are looking for the term at position 1, We don't have it because we have the simplified formula, but all we do is we plug the value of n into that variable slot. So that means that 1 becomes 2 times 1 plus 6. 2 times 1 is 2, 2 plus 6 is 8. So our term, excuse me, at position 1 is 8. So let's just plug it in to find the term at position 2. It's 2 times 2 plus 6. 2 times 2 is 4. 4 plus 6 is 10. Position 3 is 2 times n, which is 3, plus 6 is 6 plus 6, which is 12. Let's see here. Numbers is 7. Yeah. All right, and then position 4 is 2 times n, which is 4, plus 6. 2 times 4 is 8. 8 plus 6 is 14. And we need one more. Position 5. 2 times 5. 2 times 5 is 10. Plus 6 is 16. So our sequence is 8, 10, 12, 14, and 16. All right, number 9. Now, number 9 and number 11 want us to simplify, write the simplified form of the explicit formula, then find the term at position 50. So let's do number 9. They've given us the sequence 1, 5, 9, 13, which I hope you can quickly see is a difference of 4. But if you want to find that out, you take a 2 and subtract a 1 from it. And then you can take a 3 and subtract a 2, make sure it's the same. But 5 take away 1 is 4. 9 take away 5 is 4. 13 take away 9 is 4. So we're seeing that we have a difference. It is addition, so it's positive. And then we have our position at A1, which our term at position 1, which is 1. This guy right here. All right, so let's plug that into our formula. We have the term at position n equals the first term in the sequence plus position n minus 1, which is the previous position value, times the difference. So let's plug in D and A1, and we get that AN equals 1 plus n minus 1 times 4, our difference. All right, now this is what I was talking about earlier, where you see that simplified formula. You must distribute first. So it's 4 times -1 and 4 times n. And you get 1 plus 4n minus 4, because -1 times 4 is -4. All right, so then you have two common terms here. You have 1 and you have -4. So AN, now you always put your term with your variable first. This is that equation etiquette we've talked about in the past. So I'm going to go and just put the 4n in the front. And then we know that 1 minus 4 is essentially 1 plus a -4, which is unlike terms. So 4 take away 1 is 3, and the 4 is the higher value, so it's -3. So you end up with AN equals 4n minus 3. This is your simplified explicit formula. So then you use that formula to find the term at position 50. 4 times n, remember n is your position number, so 50 minus 3. 4 times 50 is 200 minus 3. So the term at position 50 equals 200 minus 3, which is 197. All right. Number 11. All right, so number 11, we have the sequence -5, -1, 3, 7, infinity. So again, we are looking at addition. So -5 plus 4 is -1. -1 plus 4 is 3. 3 plus 4 is 7. So we know that we have a difference of +4. And we know that our term at position 1 is -5. So we are looking at an arithmetic sequence. So we get our explicit formula for arithmetic sequence, which is AN equals A1 plus N minus 1 times D. And then we plug in our values. AN equals -5, which is our term at position 1, plus N minus 1 times our difference, which is 4. All right, so let's do our distributive property. Couldn't get that out. We find that -5 plus 4n minus 4. -5 plus a -4 is like terms. So we end up with 4n minus 9. This is our simplified explicit formula for an arithmetic sequence. All right, so then we use that to find the term at position 50. 4 times 50, which is our n, minus 9, equals 200 minus 9. So the term at position 50 for this sequence is 191. And those are your two answers. Okay. Let's do two more and then we'll be done. So number 13 and number 15. Number 13, in this case, we need to write the next 4 terms of the following sequences. So number 13 is -6, -3, 0. And you can see that in this case, we're adding 3. So it looks like we have another arithmetic sequence. I promise we'll get into the geometric ones on the next page. So that'll be the next video lesson. So they want the next 4 terms. So they want term the term at position A4, 5, 6, and 7. So we have, I would just use the recursive formula. So this is the term at position N equals the term at the previous position plus the difference. So that's A1, A2, A3. We want A4, A5, A6, and A7. So A4 is the term at the previous position, which is 0, A3, plus the difference, which is 3. So it is a +3. Then we have A5, which is the previous term, which is A4. So that's 3 plus the difference, which is 3, 6. And then you take that term, 6, plus the difference, which is 3, and you get 9. And then last one, 9 plus 3 equals 12. So the last 4 terms are 3, 6, 9, and 12. Number 15. Number 15 gives us the sequence -12, -3, +6. Still arithmetic. Let's get our base formula. AN equals AN minus 1 plus D. This is our arithmetic recursive formula. All right, so the term at position, we need 4, same thing, 4, 5, 6, and 7. So term at position 4 equals the previous term, which is the term at position 3, which is 6, plus our difference. So 12 to -3 is +9. So these are all a difference of +9. So 6 plus 9 equals 15. And then we have the term of the previous position, which is 15, plus our difference 9 is 21. 21 plus 9 is 30. And then 30 plus 9 is 39. So the last 4, excuse me, values in our sequence are 15, 21, 30, and 39. All right, so that's it. We will finish up the second half of this page in the next video. And thank you so much. Make sure you jot notes or put little stars or question marks by things that you want to work out with me in person. All right, see you later.